Metric space R and D. In the previous video, we precisely defined what is a manifold. If you are interested in it, feel free to check it out. Last time we still have one proof left to be finished, namely the proof of R and D being a metric space. Let us first remind ourselves what is a metric space. Definition. A metric space is an ordered pair MD where M is a set and D is a metric on M, i.e. a function that eats two elements in M and maps to a real number, such that for all x, y, z in M, a. d of x and itself equals to 0. b. If x does not equal to y, then d of x and y is larger than 0. c. d of x and y equals to d of y and x. And d of x and z is smaller than or equal to d of x and y plus d of y and z. Before we directly jump into the proof, we need two more preparations. The first one is Cauchy's inequality. Lemma 1. Cauchy's inequality. The product of the sum of Ri squared and the sum of Si squared is larger than or equal to the sum of Ri times Si squared, where all of Ri, Si are in R. Proof. For any lambda in R, we define f from R to R as the function, which f of lambda equals to the sum of the square of Ri plus lambda Si. Now, f of lambda is larger than or equals to 0 because it is the sum of the squares of real numbers. Hence, for all lambda in R, f of lambda is equivalent to, now we expand the square, the sum of Ri squared plus 2 lambda Ri Si plus lambda square Si square, which is larger than or equals to 0. Further expand the brackets, we'll get the following expression, which is a quadratic equation in lambda. Since the sum of Si squared is larger than or equals to 0, there are two cases. First, when the sum of Si squared equals to 0, since Si squared must be larger than or equals to 0, the sum of Si squared equals to 0 implies that Si squared equals to 0, which further implies that Si equals to 0. Thus, it trivially satisfies the Cauchy's inequality. Second, when the sum of Si squared is larger than 0, which means f of lambda is a quadratic function that opens upward. In order to satisfy for all lambda in R, f of lambda is larger than or equals to 0, the quadratic equation must have either one root or no root, which implies the square of 2 times the sum of Ri Si minus 4 times the sum of Si squared times the sum of Ri squared is smaller than or equals to 0. Thus, we obtain the Cauchy's inequality. End of proof. The Cauchy inequality is however not going to be used directly for proving R and D is a metric space, but for proving the next lemma, which will be used directly for proving R and D is a metric space. Lemma 2. Minkowski's inequality for sums, index 2. The reason why it is index 2 is because there is a general version of Minkowski's inequality for sums, but n equals to 2 is already sufficient for our purpose. Let all of Ri Si in R, then the square root of the sum of the square of Ri plus Si is smaller than or equals to the square root of the sum of Ri squared plus the square root of the sum of Si squared. Proof. We start from the sum of the square of Ri plus Si. Then we expand the square and distribute the summation. Here we then artificially add a square and a square root for the second term. Bear in mind that we need to change it to plus or minus sign in front. Since the term inside the square root must be larger than or equal to 0, the one with plus sign must then be larger than or equals to the minus sign one. Thus, here we can apply the Cauchy's inequality and then factorize it. Since both sides of the inequality must be non-negative, we obtain the Minkowski's inequality for sums, index 2. End of proof. Next, we are getting into the core of this video, which is proving R and D is a metric space. Theorem. A set Rn, where the elements in Rn are defined as n tuples of real numbers, equipped with a function d that is defined as follows. From two elements in Rn to a real number, we define the notion of distance on Rn through Pythagorean theorem is a metric space. Proof. A. d of x and itself equals 2, now we plug in the definition, which equals to 0. b. X does not equals to y implies there exists some xi such that xi do not equal to yi. That implies the square root of the sum of yi minus xi squared is larger than 0, which means d of x and y is larger than 0. c. d of x and y equals to the square root of the sum of yi minus xi squared, which equivalents to the square root of the sum of xi minus yi squared if we factorize the minus sign from the bracket, which equals to d of y and x. d. Starting from d of x and y plus d of y and z, we apply the definition of d, then let's Ri equals to yi minus xi and Si equals to zi minus yi. With the Minkowski's inequality for sums index 2, and reverting back to the expression with xi, yi, and zi, simplifying it, then we get d of x and z. End of proof. That is how we prove R and D is indeed a metric space.